Okay.
So last week I talked about like cosmics and stuff, as you may remember.
Well, about what?
I remember.
So I'm going to text from my family. So you might ask, why is this image so different from Interstellar? So I talked about how the accretion disk around, like here. Thank you. And how the plane, like relative to this, we're looking at the different planes. The plane that Interstellar is at is like we'll be there looking this way instead of here looking this way. But this doesn't even have an accretion disk, which is inaccurate anyway, so like doesn't even matter. I don't know. And the reason that, well, okay, I don't have a picture of an actual black hole, but that's what this image is supposed to be. That makes more sense. But this is like, but the picture of an actual black hole, it's like really blurry. I think I'm talking about that because like it's just like an overlay of a bunch of different light sources, not one thing. There's so little light that comes from black holes, obviously. That's hard to do. Hard to show. And then tidal forces, which I will be talking about a little bit today, and then a lot more next lesson when we do our first subsection. Although I guess today's kind of a subsection, but next lesson's a subsection really, where we go into Miller's Planet, which, spoilers, if you guys haven't seen Interstellar, you go to Miller's Planet, and you might remember it for like the big waves and stuff. That's what I was going to talk about for tidal waves. But I'll talk about gravitational waves today. If everything goes well. So the tidal forces would cause light from like here. This is the picture of the black hole Interstellar Gargantua. It would cause the light coming from here to like flicker in and out because gravity like changes the plane of which light gets to us. Which I mean, I'll explain gravitational waves. Basically, this is not flat space-time, and so the light won't like get to us in a flat way, even after it has gone away from the black hole and non-flat way. So the main reason that Gargantua is inaccurate to an actual black hole is because the black hole doesn't show the Doppler effect. And the movie didn't do this because the director thought that it was confuse the audience, and that to actual humans it wouldn't like really make that much of a difference. But basically, the Doppler effect is that when there's matter, it'll accrue on one side. The accretion disk will accrue on one side, and that's shown in the pictures of actual black holes. It's not shown here. It just looks like basically a perfect disk, like here, where like as close as you can get to a perfect disk for images like this. It should also be noted that the wall of Gargantua is in Interstellar. It doesn't have any quasar particle jets, which are predicted to be off of black holes, and in some cases you can tell that they are. Like you can see the matter. You can't see the matter because we don't have very many pictures of black holes, but you can see the effects of the matter far away from the black hole. So I can go into its own lesson about the quasar particle jets, but it's pretty minor, and they basically derive from differences in magnetism, like in terms of the poles, the north and south pole of the black hole. It's weird that there's X-ray to radio, whatever. I can get into it if you guys really want. Not today, but a different day. And so now I'll go over gravitational waves. In 1916, Einstein predicted gravitational waves, but obviously we proved their existence much later. But they were predicted in the relativity equations, where if a gravitational wave stretches through a medium, it'll stretch and squeeze the medium. In this case, space. It'll do this by changing from either stretch vertically and thin horizontally, or stretch horizontally and thin vertically. Einstein thought these waves would be so weak they'd be hard to detect by humans. They rise to be on the scale of 10 to the negative 17th meters, I think, which is 100 times smaller than the nucleus of an atom. So not very big. But we have found ways to detect them, and we can prove that based on understanding they're real. Yes, question.
How are they able to measure the size of a force, like with meters?
You mean how was Einstein able to predict how large the gravitational waves would be?
Yeah.
Well, it's if you recall, our plane of measurement is mass and energy. So you can tell how much of an effect something will have on a mass and energy scale. Not like a distance scale, but like on a mass and energy scale. The mass and energy tells you the distance.
Oh, okay.
If that makes sense. Okay. So I talk about inertial reference frames when I'm talking about how black holes drag them when they're spinning, where it's like a reference frame with a time scale. Particles which behave inertially will have to move back and forth with respect to each other, which is like, as the ergosphere shows, is that particles have to move like in congruence, or like they have to move in congruence with the way space-time moves, unless they go past the speed of light once they pass the ergosphere. But that's just generally even beyond the ergosphere, matter and like things warp also around the black hole in such a way. And gravitational waves are formed when these inertial reference frames collide in such a way that they produce. It's like there's a video I saw, or like a model video, but for your purposes, for purposes of this class, basically you just need to see that when they get really close, planets do weird, or like celestial objects do weird stuff, and then if their gravity's strong enough, the wells will like interpretive dance, and then all the gravity goes everywhere. This is 2D planes, so that's why, like 3D wise, it makes stuff weird, and that's what causes the flicker. There are only two types of waves that can be created in the universe, which are light waves and gravitational waves. So, obviously there are more than just two types of waves. The only ones that we created are light waves and gravitational waves. The gravitational waves are made from stuff like this, where it still conserves. I mean, obviously everything conserves mass and energy and such and momentum, but it changes the geometry. And then light waves are created when, well, I guess it depends, but like when energy goes into an atom and thus into an electron, the electron moves. Oh, I guess I could do a diagram for this. Well, this is like basics of chemistry. What is this? Let's move on. Nice.
We can start a new page at the bottom.
No, that's fine. I'll shoot over here and then move it. But thanks. So you have an atom. Remember, we hate this model, but we're using it because whatever. And then you have different states of energy, like different orbitals, as they call them. That's a terrible circle. But you understand the point. If there are 2 electrons on the shell, then it's full. The next one is 6, so it'll be. Nick, can you verify this is 6? Next. And then, yeah, 8 and then 12? Or 10? That's 10. Okay. I'm good. No, I'm good. Not for sure. Sorry, I forgot for a second. But then when these are all full, it goes up to the next one. I mean, I just explained. The next one is 8, the next one's 10. Or 12, I forget. I think it's 10. So when they move, Nick, you already know this, I assume. The light stuff? Yeah. When you move from one state to another, that means your energy level is changing. The states are not physical states; they're levels of energy. And also, these are not particles; these are particle waves or wave pools because it's electrons. This is an atomic. This is an atom, so everything's complicated. But we can see it as particles. Say it's whatever. And basically, when you have different ladders, like imagine these 3 or the 3 circles here, the 3 orbitals. If there's an electron here, well, all electrons want to get to the lowest orbital possible because they want all energy wants to be probabilistically the least in the universe, and that's why entropy happens, which I think I explained a few weeks ago. That has to do with the same probability stuff, but when it goes down, like it's at a higher state of energy here, and so when it goes down to a lower state of energy, because it wants to go to a lower state of energy, where does the energy go? Well, it's transmitted in a light wave, and that's what we see. That's all the stuff we're seeing is when light doesn't bounce off of atoms, it gets absorbed and then changes the energy level, and then it goes to us. And the wavelength of the light, basically like what color we see, is dependent on the distance between these three things, because they're different depending on the atom. So that's what causes all the color we see. And yes, question.
So is that like when plants absorb, like plants do photosynthesis, they're absorbing the light and then they're going up, and then to go back down, they release every other like receptor gene that they can use?
No, the opposite.
No, they're absorbing everything.
They're absorbing light energy. They're not they're absorbing. I guess they're absorbing color, but they're absorbing energy from the sun through heat and through sunlight. And then when they try to go to a lower energy state, because they always will, or I guess I shouldn't say that.
They have more to release.
They release at a specific wavelength.
Oh.
And the green is the best. Green just happens to be the best for that specific type. But like, if we just saw different colors, then it wouldn't look green to us.
Like
So,
carrots make different, so they look different.
Like what?
Carrots look like orange.
Yes, but they grow underground. Yeah, question.
So the light, the colors that we see are the actual original colors that the light was. It's like
Yeah, everything we see is a reflection of everything else. Like the only thing we actually see that comes from the original source is when we stare at the sun, which you shouldn't do. But it's so bright that it burns red in those because there's so much energy and color and joy. Yeah. Any other questions? Or does that enough to answer your question?
yeah.
Okay.
Isn't there a theory that you're not ever really like, I don't know if it's a theory or a real thing, or just something I saw on YouTube. Like you're not ever really touching something because there's kind of like a surface.
That gets a little freaky, but yeah. Yeah, you don't really, I mean, the thing is that like at such sizes, whether you can touch something is irrelevant because nothing is touching anything, and nothing is really nothing. Nothing's really nothing, nothing really touching anything, so the distances between what is matter and what's real, like what's the difference between, or sorry, what's between an atom and another atom if there's nothing there? There's nothing.
Yeah.
So they're touching.
Okay.
Because they're like, it's just, yeah.
How many times do you think the tunnel effect has happened? Like ever in the entire universe?
What do you mean the tunnel effect?
Ever.
Where you can like interact with an object and there's a chance that your atoms perfectly in line.
Oh.
Whoa.
I don't know the probability, so I can't give an estimate.
Of the entire.
You can look it up if you want, and I can do a fake calculation in my head to approximate it in my head if you want me to do it like a circus class.
Okay.
Or you can look it up yourself.
Wow, so aggressive.
Just saying.
How many times have I had to hit this table before I hit it? That's the real question.
That is a good question.
Okay, next section.
Will the table break first?
So the final act of Interstellar, spoiler alert again, the Endurance attempts to slingshot around Gargantua. Where's new page?
I think it's at the left, on the bottom near the one.
This one?
No, in the middle.
In the middle of the thing. To your right.
Am I stupid?
Middle.
No.
Down.
Oh.
I think that's the new page.
Sam, it says the chance is 1 in 10 to the power of 10 to the power of 30.
So that's more atoms than exist in the universe. So I'm going to say 0 times. Okay.
Good question.
And it's probably more atoms than have existed in the universe in every moment of time, if you break up every moment of time into the smallest, like a Planck length of time.
Planck.
Yes. Which, how did I talk about that? I thought I talked about that something.
Planck.
I remember what you talked about.
Okay.
Oliver talks about that.
He did? Oh, at the house or?
No.
Oh, just in general?
Yeah.
Yeah, okay. So, I want to, basically I did a project last year, and Mr. Bergman told me I had to like do something that actually was related to what we're actually learning instead of just doing, black holes. You don't learn that in physics. So, or like in AP Physics 1. So I was like, okay, I'll do the escape velocity calculations for the black hole because they actually do that in the movie. So in the movie, they attempt to do an escape of the black hole by going like around the black hole, but if I'm frank, that's too difficult for me to calculate because if you think about what's happening, you're basically finding the geometry of the black hole with only the information they provide you from the movie. When it's an advanced like postgraduate school level calculations with linear algebra, and I didn't even know calculus when I did this. So I decided not to do that, and I instead found the simple escape velocity, which is that they were going directly away. But as you'll probably remember from physics, if you're doing an angular velocity escape, it's less than a direct velocity escape, which Josh will remember that. And that means that I found basically like the upper bound of what it could be. So also I should note, I was going to put this at the end, but yeah, I'll talk about it. There's something called the Penrose process. So if you remember in Interstellar, it's a big plot point that Cooper has to like sacrifice himself to like leave behind himself. Yeah, he didn't have to do that. So the Penrose process is theorized as a way to use the frame dragging effect I talked about to create energy and thus velocity for an object in the ergosphere in exchange for the rotational velocity of the black hole lowering. So basically you just use the black hole's rotational velocity and then you make that your own velocity. And it's theoretical, but like it would have done no harm if they just did that instead of sending Cooper, and it would have been Cooper would have been alive. Or I guess he was still alive, but he would have. They assumed he would die, so yeah, whatever. They could have been used by the Ponce of Endurance as a means of escaping Gargantua by sacrificing fuel and unnecessary parts of the ship. Although it seemed as if they were unaware this maneuver was possible, and they chose to sacrifice Cooper instead. So like whatever, like.
It was for emotional effect.
Yeah.
It was for emotional effect, and I actually didn't cry that part. I cried the part after, and probably throughout. It was very good.
What part?
Don't say what part. Mine is.
Are you gonna finish it?
Yeah.
Wait, you haven't seen it?
I haven't finished it. Remember?
Have you gone to the part I just talked about?
No.
That's what. Okay, whatever. But you're fine that I spoiled it, right?
Yes, no,
okay.
it's fine.
Okay.
Wait, we should just do a watch party.
Yeah, we should.
Okay.
If you have,
You all come.
you should bring more cookies.
No, you're good. So,
Cracking popcorn?
excuse me, I'm trying to get presentation. Okay. So, basically, I found the escape velocity. We basically just did this in physics anyway. You did this like years ago, but we do it in physics anyways. But I'll show the derivation of it just to show you guys. But
Oh, yeah.
so you can. I'll derive this. So have any of you guys, except for Nick and Josh, I guess, if you're paying attention, any of you guys taken physics? Okay, well, this will be a little bit new for you then. That's okay. So basically, kinetic energy plus
Gravitation. I actually don't remember.
potential energy initial
Yeah.
equals kinetic energy
Oh, God.
final plus potential energy final. So basically, what this tells us is that energy is conserved. This is basically explaining potential and kinetic. Kinetic is the energy of. Oh, I already explained this actually. The energy of movement, and the potential is energy of like if I'm holding this, then it has the potential to do that. Whatever. So when you set we set potential energy to be gravitational potential energy because we're assuming there's no other potential energy because, like, what would there be? It would be, we just replace the E with the G, and it'd be fine. But, like, I don't want to do that because it's complicated, or it's just annoying. Yeah. So, when you set those equal, you can see that, or you find that the final kinetic energy is equal to 0 because you're just trying to get the minimum amount of energy you can go to get there. So this is the energy you end up going. So like once you get past this, like this is before you escape, after you escape. After you escape, you're not trying to move anymore. Like you could, but you're not trying to move anymore. You just kind of go however gravity takes you. And you also find that the initial gravitational potential energy is also 0. So it becomes KE initial equals basically like that. And then, oh, and the, wait, hold on. Oh, wait, sorry. No, there's a lot of gravitation potential. I'm sorry, I was mistaken.
Okay, cool.
Yeah. And there's no final gravitational energy because if you think about it, you're no longer potentially going to the black hole, so it becomes plus UG initial. So basically, you get this one side, you get K E equals negative UG, and that means that you get
Damn. Rounding.
unfortunately equals holy moly, I forgot. Okay, there we go.
Sorry.
Okay. So it's negative of this is also negative. That's why I simplified it, but I figured to show you that the potential energy of gravity is negative, and then it's negative times that, so it's just a positive. But like in case you didn't know. So then, if you get this to one side, which I'm not going to do, it's literally just like algebra 1. Then you get that thing up there, which you could probably see. So that's how we get the equation for speed velocity, and then can I just yeah, so you do that, and then you get velocity equals, oh boy. Approximately this. I had to do sigma because Christina taught me, and yeah, basically that's how fast you're going to escape the black hole. And that's about 4.6% the speed of light, which doesn't sound very high, but that's 72 times faster than any man-made object has ever traveled. Which the thing that traveled that fast was NASA's Parker Solar Probe, which reached the velocity when it was approaching the sun, and it was also like the size of me, maybe. I actually don't know, but I assume it was very small because it has to achieve that high of a velocity. And if that happened, then the whole thing, this thing should basically break apart. The Endurance, the ship, should break apart. I had when I originally did this project, I had a partner who researched the Endurance while I researched the black holes, and I can check their paper to see if they actually looked at whether the ship break down. But they're more so looking at the. Well, actually, I guess I shouldn't spoil it since you haven't seen it. It's not relevant to this. But after you watch it, I'll tell you what they were looking into. But it's after what the events of this stuff. So, what do you mean whispering? They did the post black hole thing. They did like whether that was feasible.
Oh.
Yeah. Which I don't know if you remember that, but yeah.
I don't.
And next week we are doing Miller's Planet, so get excited for that. And other than that, I am done for this week.
I don't know.
I guess on schedule because I expect it to start a bit later. But yeah, any questions?
Yeah.
Oh wait.
Yeah.
Can you summarize what I missed last week?
There's a video. I posted the video so you can see.
Oh, yeah, but I saw it at the day of, and I was like, oh, I should watch that. And then I was like, oh, but I'm still throwing up.
Oh.
That's a good
And I
excuse.
forgot.
I'm not saying she should have been here, but I'm saying I posted this so that she could. Anyway, you had a question.
Completely unrelated.
Can you save it for the end now?
Okay.
Is it?
We got 1 minute, so I'll listen.
Bye-bye.
Bye, Nick.
Bye.
Have you read The Martian?